I'm starting the broadcast. Ok, então a gente já está ao vivo. Olá, pessoal, obrigado por todo mundo que está aqui presente hoje. Nós estamos num ciclo de palestras muito especial para celebrar os 20 anos da disciplina de Laboratório de Métodos Ágeis do Instituto de Matemática e Estatística da Universidade de São Paulo, que é um dos cursos pioneiros no tópico no Brasil e no mundo. E para celebrar isso, nós estamos convidando palestrantes muito especiais, e hoje a gente tem o prazer aqui de receber o Grady Booch, que ele é cientista-chefe de engenharia de software na IBM Research, né? Ele é criador aí do termo design orientado a objetos, né? Co-autor da linguagem de modelagem unificada, o famoso ML, né? E membro fundador da Agile Alliance, né? Tipo, maior associação aí mundial do assunto, e também da Hillside Group, que costuma trabalhar bastante com padrões de projetos, né? E, além de tudo isso, né, ele é um expoente na área de arquitetura de software, né? Então, feitas as devidas introduções, eu vou repetir essa introdução em inglês, para se a gente tiver aí alguém de uma audiência internacional participando conosco, e repassar todos esses pontos. So, hello everyone, and thanks for your presence here today. Today we are celebrating 20 years of our Agile Methods Lab course in University of São Paulo in the Institute of Mathematics and Statistics, which is a pioneer course in the subject in Brazil and both worldwide, one of the first courses of its kind. And today we have the great pleasure of receiving Grady Booch, who is a chief scientist at IBM Research, is creator of the term object-oriented design, is co-author of the famous Unified Modeling Language, the UML, and a founding member of both the Agile Alliance and the Hillside Group, which are associations with are key in the fields of both agility and design patterns. And of course, he's an exponent in the software architecture field. I'm here with my colleagues, Professor Fredo Goldman, Tatiane, and also we have the pleasure to receive Joe Yoder, who is also a very strong person in the community of patterns. So, Grady, please, you have the word.
Thank you very much for having me. One day I hope to be able to visit your delightful, beautiful city. COVID has stopped everything, of course. The last trip I took was in 2019, and I really miss traveling. But, you know, I'm not in a bad place. I'm in Maui, Hawaii. It's sunny. I've got palm trees outside, so I'm doing okay. I spend about 20% of my time as an architect on one of the largest software-intensive systems I've ever been in my career. It's a federal project. I spend another 40% of my time with customers on various projects, mostly in the realm of architecture, ranging from everything from next generation auto systems to financial systems, dabbling in some interesting fintech things that touch upon the areas of cryptocurrency and the like. And the rest of my time, I'm actually engaged in some really interesting AI work. That's why you see the little robots behind me. This one in particular, a humanoid robot here, Pepper, we've been using on some work with the Johnson Space Center at NASA. In fact, I am IBM's senior representative to NASA, and I'm trying to bring us back to space. So needless to say, I'm kind of a busy guy. I've actually got a couple of books underway as well. But today I'm here to talk to you about some of the past and some of the future. Now, why should you care about this? I absolutely celebrate the focus your organization has on agile methods, because that is certainly the dominant way that the software industry, build software intensive systems these days. But in order to understand where we might go next, it's very useful to understand where we have been, and thus the focus of today's presentation. We'll talk about some of the history of software engineering. We'll talk about its present. We'll talk about some aspects of software architecture, and I'll project out to where I see the world going. Let's share some slides here. Here we go. So first off, please know that I am eminently accessible. You'll find that I respond to all emails. I follow me on Twitter. I usually have some lively discussions there. Can you see this one now? Is that, yes, it's good. It's up and running. There we go. So so follow me on Twitter if you wish. There's my website where I'm doing some interesting things. I'm noticing the screen looks kind of dim. Is that dark enough for you all? Let's go to another slide. It is very
Perfect.
dim. Oh, it is good.
Yep.
You can see it well? Okay.
Everything okay.
Good, good, good. Okay, good,
Yeah.
good, good. Technology sometimes confuses me. You know, as software engineers, we come from a really wonderful legacy. Imhotep from Egypt is probably the first engineer. And if you think about it, we come from a great legacy in that he was a high priest of the sun god Ra. Now, how cool is that? We are descendants of the priests of the sun god. That's pretty neat. But there's some other side of this. If you jump forward to the 19th century BCE, you realize that builders had responsibilities. As the code of Hammurabi said, if a builder builds something and somebody dies, well, we're going to kill you too. Thank goodness this doesn't happen in software, because we would all be probably not around anymore. So the point of this, though, is that as a software developer, as a software engineer, it is both a privilege as well as a responsibility. As we also look back in the past, another candidate for being the first engineer is Ismail Al-Jarazi. He's the first pattern language person. He wrote this, actually it's perhaps a number of brothers. They wrote this delightful book called The Book of Knowledge of Ingenious Mechanical Devices. It basically said, hey, if you want to do this thing, then here's how you might build it. And so it was the first patterns language book. Well, where did the idea of engineer come from today? Turns out it was in the 1900s. So here we are at the turn of the century, the turn of the last century, previous century, and people were building really large projects. We were building dams, we were building intercontinental railways, all sorts of things like that, and they were failing. Dams collapsed, boilers exploded, people were dying, not a good thing. So of all things, the state of Wyoming said, we need some accountability. And that accountability was in the form of having licensed engineers. Charles Bellamy was the very first. So to that end, that's the hardware engineering side of it. But we began to find, especially around World War II, the end of World War II, that there were these really complex systems that had lots of moving parts. They had engineering associated with mechanical devices, chemical devices, nuclear devices, and increasingly software devices. So the term systems engineering came back to Bell Labs in the 1940s. Well, engineering is largely what we call an occupational closure, meaning that to be an engineer, you've got to graduate from a certain college, an accredited one, you've got to pass an examination, and you have to have experience working as an apprentice. We don't do that in software. We just sort of say, hey, I self-declare myself as an engineer. Now, there have been attempts. Canada, for example, under the work of Philippe Kruchten, began licensing software engineers. The state of Texas did so. But in the end, every one of them gave up. And so that's a good thing and a bad thing. We as a discipline are still very, very young. And yet there is an important element of having discipline in our organization itself. So really, we're a very young domain. The idea of computers themselves, well, you know, for the most part, the earliest computers we didn't see until the 1800s, and most of them were human and most of them were women. The term digital did not get invented until 1942. George Stibitz did so. And indeed, the term software didn't come about until 1952. So we are an astonishingly young discipline. Where did the term software engineering come from then? Well, Some say it came from the NATO conference. So here we are in the 60s, and the US at least, well, and Europe, was experiencing what they called a software crisis. And so a conference was formed. Bauer used the term software engineering as kind of a play on words. He was being a little bit trolling here, and he was saying, hey, we're doing something a little bit different. Turns out wasn't the first use. In 1966, there was an editorial, a letter in the communications of the ACM, in which the president used the terms to distinguish one from another, speaking of it hardware engineering and software engineering. Because remember, prior to that time, it was just computer engineering. You didn't really distinguish between the hardware and the software side of it. I found it even earlier, and I tracked down this classified ad in a journal, Computers and Automation, from San Jose in 1965, which was the first appearance I found of the term software engineering in that literature, looking for a software engineer. Turns out it goes back even further, and it goes back to Margaret Hamilton. Margaret was the first, one of the developers for Sage. We'll talk about that in a bit. And she was a lead developer for Skylab and Apollo. And to distinguish what she was doing from all the hardware engineers around her, she called herself a software engineer. Margaret, I declare to be the originator of the term software engineering. We'll see her again in our history. Is what we do in art or a science? Well, it's a little bit of both. Grace Hopper, says it's a lot of an art to it. Donald Knuth believes it is to be as well. Frankly, I like what David Parnas said. It's really both. That we apply engineering techniques to creative techniques that bring together software engineering and indeed systems engineering. Another reason I like to speak of it as an engineering problem is because if you think of a civil engineer who's building a building, they've got to deal with dynamic forces, wind, earthquakes. They've got to deal with static forces. I've got people in the building. I've got equipment in the building. And I try to build a system that is not only pushing back against those obvious forces, I've got to do it within budget on a certain time schedule, and I'd like it to be beautiful if at all possible. I'd like it to be maintainable. These are the aspects of a system that put the forces on the system, and as an engineer, be it a hardware engineer, a civil engineer, or a software engineer, you're trying to build systems that reasonably optimally push back against those forces, both static and dynamic, so that you have a system. That's our goal, to build that are useful. Now, this should resonate with you from an Agile perspective. We've got lots of terminology and ceremony around what Agile is, but I think it all comes down to this. And this is something that my dear friend Bran Selleck wrote literally on the back of a napkin at a restaurant once. On the x-axis, we have time. On the y-axis, we have focus. Every project, every successful project does this. There is a period of discovery, that's the red. At the beginning of a project, you don't even know enough to ask the right questions, so you're discovering. Then there is a period of invention, that's the stuff in the purple, where you say, I now know enough, so I'm going to make a conjecture as to what it is I should build. Then there is a period of implementation, that's the green, in which I'm actually taking those things I've discovered, making the decisions I have found, and turning them manifest into real life code. Every successful project has these overlapping cycles to them. Whenever I get parachuted into a project, there are a number of questions that I will ask. One of the first of which is, tell me your rhythm of releases. If they tell me, yes, we're using Git or some appropriate repo, and we build continuously and we do a release every day at least, and we do regression tests on it, that's a good thing. Tells me that your project has a good rhythm associated with it. And that's what I mean by the sort of electrocardiogram in the bottom. It's also the case that you will see these periods of what are called punctuated equilibrium, periods of stable releases that then people build against and incrementally improve. Every project is like that. That being said, there's another way to look at this, and it is from the perspective of decisions that are made. So again, I've got the rhythm. The x-axis is time, the y-axis is, think of it as intensity. And at every moment, I am writing some code. I am making some decisions. Those are the green lines here. At the beginning of my project, there are so many decisions to be made. And indeed, I'm going to keep making those decisions along the way. Sometimes I'll reverse those decisions because we've discovered certain things. Some of those decisions are particularly significant, and that's what architecture is. Architecture, well, all architecture is design, but not all design is architecture. Architecture represents the most significant design decisions, where significant represents a cost of change. And so in red, you will see the accretion, the growing of those architectural decisions. They'll peak at the beginning of the project, but as you discover new things along the way, you will refactor them. You may refactor them in the small as part of your MVP, your minimum viable product that you then keep releasing, or you might do it in the large. Netflix, for example, has gone through 4 or 5 major architectural transformations. Photoshop, its first version was implemented on the Macintosh. In fact, if you want to, go to the Computer History Museum and you can see the original source code for Photoshop. They've gone for 5 or 6 different incarnations. In their most recent one, they're actually starting to move things so that parts of Photoshop run on the cloud. What's astonishing, though, if you look at both of those systems, you will find design decisions that they made at the very beginning that are still there. In Photoshop, for example, one of the key design decisions was we're going to break apart the things we operate upon into these tiles. Still exists. If you look at your typical software development project, at least in pre-COVID days, it looked kind of like this. I won't tell you what company this was, but it's a Silicon Valley company. Pretty typical, lots of monitors. You'll notice there are different machines, some Macintoshes, some PCs, some Linux devices. My first reaction upon seeing this was, where do they hide the women? Oh, and therein lies a story. Because our story really begins way back in the 1800s with, of course, Babbage. Now, in Babbage's time, we didn't have anything such as software, although Ada Lovelace began to hint at the notion of it's different. In fact, she's considered the first programmer because in 1842, she proposed that what Babbage was doing was interesting, but there was a way to address these symbols that meant much more than just mathematics. So she was the first programmer in the sense that she saw that level of abstraction. Boole, around the same time, was making the outrageous assertion that we can define the laws of thought. Now, a little bit of hubris with that, because he's basically saying we can formalize what thought is. Well, pragmatically, what came out of this was Boolean logic, which turned out to be pretty important to us. The first programmers you would see here, and in fact, the first programmers were often women. This looks like a typical stand-up meeting, doesn't it? You've got the developers sitting around doing the real work while the managers in the back sort of shouting at them. The person in the front is an important character in our history. This is Annie Jump Cannon. She is a programmer, and she and her colleagues worked at Harvard, in particular the Harvard Observatory, and they were the Harvard computers, because back then a computer was simply a term for he or she who computes, and these were mostly women at the time. What's interesting about this project is that the foundations of Agile we saw being laid in the 1800s, because they would be given a task, in this case Pickering, and the gentleman standing on the left-hand side, and the women would self-organize themselves. You had self-organizing teams even a couple of centuries ago. So Annie we can think of as one of the first human computers. In many ways, she's the spirit guide to Agile computing, if you will. When mechanization came into play, what was remarkable is the women were still there, but now they were a little bit more organized. Pay close attention to what's in front of the women. You'll see that there's a tray, and what would happen is that they'd be given some task. With that device, they would do some operation, the same operation over and over again, which was usually just an addition or subtraction. You couldn't really do multiplication on them. They would take the element on one side, do the multiplication, or so the addition, subtraction, pass the card over to the next. This is a pipeline architecture, and this is how computers got organized when computers were human. So around this same time, there were a couple of people, Frank and Lillian Gilbreth. If you've seen the movie Cheaper by the Dozen, that's about their family because they had 12 kids. Frank and Lillian Gilbreth were what we would call, oh, I'm not sure the right phrase. They studied how people worked, how literally they worked. How would a bricklayer lay bricks? And they did these time and motion studies where their goal was to create efficiencies within them. Now, this was very dehumanizing, but on the other hand, it led to an idea called process charge, which we'll see again. As the machines became more expensive, a really interesting thing happened. We saw more machines, we saw we needed fewer people, and all of a sudden the women got pushed to the side. So we saw the beginnings of how computing was changing the social dynamics of our lives. Same kind of pipeline process though. So Gertrude Branch around this time and J. Presper Eckert, you may remember his name from the Eckert-Mockley Corporation, they were beginning to devise methodologies. In fact, there's a great book that Eckert wrote on punch card methods, which was perhaps the first methodological book. If you want to do this kind of payroll operation, then organize your punch cards this way. If you want to do this kind of statistical analysis, then do it this way. A pattern language plus methodology. As we moved to the time of World War II, the stakes were much higher, in which we needed to do computations that were larger, they were at scale, they were faster. This is the Harvard Mark I. And the woman on the right-hand side, she may look familiar to you. That's Grace Hopper again. Because she came up with the notion that, we really need to separate our machines from our software because the software itself is becoming awfully expensive. So George Tibbets, you may remember him from an earlier discussion, he began to take Boole's idea and realized that we could take that logic and implement them in relays. And thus was born the theoretical underpinnings of the electromechanical computation that came about with Howard Aikens and George Tibbets's work with the Mark II. Grace was on the project looking at it from the software side. In a different world, if the war had come out differently, I'd probably be talking to you in German and we'd be studying the works of Konrad Zuse. But we didn't, and the West won the war, and yet we did not hear of this device until 1972. This is the Colossus. If you've seen the movie about Turing, it was a great movie with Cumberbatch, wonderful cinematography, great acting, terrible history. It's as if Turing solved everything. He didn't. He did come up with some of the theory behind the Colossus, but it was the engineer Tommy Flowers that built it. So what you've got here is a vacuum tube computer that was used to solve the Lorenz code, and it was fundamental in helping win World War II. But it was kept secret until 1972. It was during this time that we began to better understand how to do programming at the level of plug boards. It's kind of looked like this. So in fact, in the US, we had the ENIAC happening around this time. Same situation as you saw with the Harvard programmers, that you'd have the mathematicians that would say, hey, we want to solve over to a set of women. In fact, it was these 5 women in particular, the main programmers for the ENIAC, who were given the task of taking those equations and turning them into executable programs on the ENIAC. They self-organized. Again, another agile team, and women were there to do it first. If you have a chance, go study some of their oral histories. They're all available at the Computer History Museum and other sources. Well, now programming was becoming a thing unto itself and becoming a little bit harder problem. Maurice Wilkes and Stanley Gill together implemented the idea of a subroutine. Now, you think about it, subroutines are part of the oxygen that we breathe, but in their day, they were considered extraordinarily controversial. because they were computationally very, very expensive. But they certainly began to understand the growing complexity of our systems made it such that we had to begin to abstract. And this was the first signs of algorithmic abstraction. John von Neumann, in front of the Johnniac at the time, he was beginning to explore some really large problems. In fact, the earliest elements he dealt with were programs to deal with nuclear simulations. He was involved in the Manhattan Project. He was doing weather forecasting. He was doing artificial life. And all these things required abstractions that moved higher than the level of the machine itself. So the problem became particularly important when we started seeing non-programmers needing to develop code. And thus came on the scene the work of John Backus and the development of Fortran. So in around World War II again, he and his team began to develop languages that were far more expressive, again, moving up the level of expression, of abstraction. Indeed, it's fair to say that the entire history of software engineering is one of rising levels of abstraction. Goldstein and von Neumann worked together, and they took some of the ideas of process charts. They were influenced by the process charts ideas from Galbraith and formed today what we call flowcharts. So again, algorithmic abstractions. As we moved to the 60s, late 50s, 50s, early 60s, then we were in this funny stage where we had both punch card devices on the right, together with more electronic devices like you see on the left. That's a Ramek, a hard drive, a number of platters. If I'm not mistaken, that particular device, which weighed about a ton, I think it stored around 10 or 20 megabytes of storage. Not a lot. I mean, you do a JPEG these days, and it's bigger than that. But the problem with software was increasingly important. And so Pinkerton came along this time and said, you know, I see people doing the same things over and over again. So had not yet unbundled software and hardware. So they were making money off of machines and could really care less about the software. So thus was born the first open source software groups, a group called Share, a group of IBM customers primarily, where they would literally share code. Oh, you've got this routine for a binary tree. Hey, great. Here it is. Let me use it. And here's the deck of cards to do so. First open source software. In the 50s, we also had this phenomena of the Cold War. So what you're looking at here is the SAGE, the semi-automatic ground environment. In its time, it was the largest software project on Earth. So the threat was the United States of the Russians taking their bombers and coming up over the Arctic and bombing American cities. So we built a set of radar across the Canadian border and really across the north. And all those signals were fed into these control centers throughout the United States, the SAGE centers, where operators would sit in front of those consoles in the back, the circular things, and they would watch for radar traffic. And all that data was fed in here. This was the largest software project in its time, and it was from this that the ideas of the software crisis was born. It used, I think they told me it took somewhere around 30% of all programmers in the United States were working on this. And so we were now in the realm of, it's not just business or scientific software, we're dealing with real-time stuff. We're dealing with larger systems. And so that's why Jay Forrester, who invented some of the technology you saw in the back there, Bob Evans in the management of projects like the IBM System 360 operating system, we began to see that there is a discipline needed not just to program, but also to organize these things. And now here we are in the 60s. We're really in the golden age of software engineering, the first golden age, because now the economics were such that you had what evolved we call a programming priesthood. In effect, you would find because the machines were so costly, we would optimize for their use and we would throw programmers at them. So you'd have programmers off to the side who would take requirements, they would write the algorithms using flowcharts, they'd pass those over to mostly women who would punch card them, write the punch cards, they'd carry those punch cards to the front desk of the computer room and they'd run them and then come back later. So very much batch processing. And so the problems here were as our software became larger and larger and so expensive to run them, then we needed better ways to deal with that complexity. Thus, we have on the scene in our first generation, first golden age of software engineering, folks such as Fred Brooks, and I'm sure many of you have read his books, Larry Considine and Edgar Dijkstra bringing us the ideas of structured programming. On the edge, there were some interesting echoes of things to come. O.J. Dell and Christian Nygaard were exploring the ideas of object-oriented stuff, hadn't quite made the mainstream. Tony Hoare working on formal systems, again on the edge. But the real mainstream work was with people such as Margaret Hamilton, who's standing in front of a set of printouts from the Apollo project. So here we are in the 60s, dead in the center of the first golden age of software engineering, in which structured analysis and design techniques were the fundamental kind of thing going on here. Now, one output of the space program and the space race with Russia and the Cold War is that we saw miniaturization, and that changed the economics of our software systems. So we saw the rise of mini computers, which now meant that a single or two programmers could use an entire machine just by themselves, and they're relatively very, very powerful. And so this is where the ideas of abstract data types from Barbara Liskov came into play, Parnas's information hiding, Peter Chen's ER modeling, and Win Royce. I had the delightful opportunity to work with Win on an early project at Lockheed. It would have been in the 80s. Win wrote this paper, of course, on waterfall methods, a much misunderstood paper, because he really wasn't advocating waterfall methods. He was basically explaining this is how you shouldn't do it. And people associate his name with it, but read the paper. You'll see he had a lot of nasty things to say about waterfall. And so here we have the greats of structured analysis and design. Doug Ross with SADT, Constantine, Jordan, Michael Jackson, Tom DeMarco. These were the rock stars in their days, dealing with the problems of how do I break apart these large kind of systems. Now, John came on the scene as well. He had done his work with Fortran. He was made a fellow and sort of said, hey, you can do what you want. He began to work in the area of function, which we've seen has come back today for certain reasons. Why did FP not succeed? I had a chance to spend a day with him doing an oral history, and he said, well, you know, Grady, the problem is functional programming allows you to do hard things really easy, but it's really hard to do the easy things. And then, of course, the microcomputer and the PC came on board, and all of a sudden, everybody could become a programmer. And we saw languages such as Object Pascal, Algol, C in particular, and then eventually C++ come onto the scene because they were the right kinds of languages at the right time. And then you had these three rogues come into play. Wow, what a time. Here we were at the second great age of software engineering because we were at a very interesting change. The internet was just coming into being. I got my first email address in 1979, of all things, when it was part of the ARPANET. We saw the rise of really complex distributed systems that were essential to organizations. We saw the rise of the web. We saw the rise of things on the edge itself. And it was very clear that we needed to look at the world in a different way. Well, Jim, Ivar, and I, of course, had our own methods. And the way we came together was, quite frankly, for very legitimate economic reasons. OMT, Jim's method, and my method were perhaps the most popular. And so we said, hey, let's hire Jim. This is we being rational. And let's have Grady and Jim work together. So we did. And then about a year later, because both Jim and I had adopted the idea of use cases, and we were doing some interesting work with Ericsson, which is where Ivar's work was emanating from, we said, hey, let's buy Ivar's company. And thus was born the collaboration of the three of us, which led to the UML. Now, it's not just us. We happened to end up on top, but there were literally hundreds, if not a few thousand other people who were in this vibrant place. Stephen Meller with his work, Ed Jordan came back on the scene, Rebecca Wurst-Brock with RDD, Pete Code as well too, a whole host of people who were laying the foundation for what became our current age of software engineering. Let me skip for a few here. The other interesting thing was happening is we also saw the foundations being laid for things like clean code. Really, the ideas aren't from Martin, but they come from Donald Knuth in his work of literate programming. The idea of open source software we saw back with the Share project, but Richard Stallman brought it front and center with his work as well. And now all of a sudden we're in the age of the internet, and all of a sudden our early systems began to look like this. They were loosely connected, which is great, as all systems should be. But now the programming problem became more difficult because programming distributed systems is just plain hard. And this was the era in which techniques such as Scrum programming, extreme programming, ideas of refactoring, and what became formalized in the rationally unified process came to be, because we were dealing with software development in an industrial strength way. Why does that name on the right side look so familiar? Because Walker is the son of Win Royce, the gentleman we saw earlier and talked about with regards to waterfall methods. Walker worked primarily on agile methods. In fact, speaking of agile methods and such, this is when the Agile Alliance came to be. I would have been one of the signatories to the Agile Alliance, but up in Snowboard, but literally that week I got called away to work with the customer and wasn't able to do it. So unfortunately, I didn't sign on the dotted line, but I was there at the beginning. The Hillside Group, one of the earliest patterns group, came from an experience that Kent Beck and I had. So Kent and I were doing some similar things. We said, hey, let's put together a workshop. We invited all the usual suspects working in the patterns community at the time to a place up in Colorado. And we were all standing on a hillside in Colorado, beautiful, crisp summer day, and we were reading from Christopher Alexander's book on design patterns, or his work that became design patterns. And we had this revelation, and that's why we call ourselves the Hillside Group. Mary Shaw took it the next level and said, you know, it's not just patterns at the programming level, but we also see patterns at the architectural level. Then the world changed again when we had mobile devices, because all of a sudden the power changed, and now we were dealing with devices that were extraordinarily computationally intensive on the edge. The earliest architectures were simple client-server ones. We do things on the edge, we throw it over the wall, but now we've discovered that there's greater interactivity that's possible between them. So around this area, this is when the Agile Alliance came to be. You saw the rise of Git, of the ideas of Stack Overflow. Jim Copleen took the ideas of patterns and brought them to organizations themselves. Again, a very vibrant time. But economics were leading us to this maturation of the web. We saw the movement toward the cloud, where the economics of on-site versus cloud systems were pushing us in the direction of cloud. And that's a good thing itself. And so in the light of that, this is where Devops came to be. Andrew and Patrick bringing us the ideas to it, where they realized if you're going to build these kind of systems, you have to look at it from a cross-cutting set of cross-cutting concerns from the perspective of the network as well as the software itself. And that's really what Devops is. Economics has pretty much led us to this. And what you see here are these walled gardens. First great example of this is Salesforce. Salesforce is the dominant SaaS company, software as a service. And so they devised their business around a set of services, APIs, that you basically run your business on. That's cool. Pretty much everybody is doing this these days. Amazon in particular. Now they're a great example of how to make architectural decisions that stick. In the earliest days, Bezos said to his team, everything should be a service. Now they pushed back against it because that was the day that was pre-SOAP, simple object access protocol. So early days of distribution within internet systems. But he insisted, and they did so. And from that, they then began to realize some significant economies of scale. The first thing it allowed them to do was be able to create Amazon retail stores. So I'm a Gerber baby, and I want a Gerber baby business, and I want to sell things on Amazon. I want it to look like Amazon. I want it to do it as if it's with Amazon, but really I want to populate it. And that's the idea of the Amazon stores. They did so because you can separate those semantic pieces of the system through a set of APIs, sort of pass those over to your retail customers, and it integrates well with Amazon itself. They did the exact same thing with what became their cloud services, AWS, because it was logically separated by a set of services. It was easy to separate and sell those services to customers. So this is why we speak of this is an era of platform computing. Bezos did it with Amazon. Jeff Dean pioneered it for Google. And it was the way that pretty much everybody was doing business as we saw at the turn of that century. What came from that, of course, was the rise of a variety of platforms, or a variety of frameworks, Kafka, RabbitMQ, all these kinds of things emerged from it because they were common solutions to common patterns. So let's pause. Where are we then? This is sort of the age we're in at this moment. That on the one hand, we have a lot of these web-centric systems at scale. And for the most part, we kind of know how to organize them. There are common patterns associated with them. The most common pattern emerging these days is, of course, around containers and Kubernetes. When I put my video back on a bit, you'll see a little cluster behind me. I've got a cluster of 4 Jetson NVIDIA Nanos running Kubernetes, and it's basically a supercomputer on my desk. It's pretty amazing. So we kind of see what's moved in that direction. Now, keep in mind, not everything is a web-centric system at scale. We've got hard real-time systems, we've got avionics systems. So there is a world beyond just cloud, believe me, but we're still in a reasonably stable place there as well. What's happening next? Well, here's a good way to look at it. On the left-hand side, we have our imagination. On the right-hand side, we want to turn that into software that actually executes. So the question this slide is addressing is, what separates my imagination from my implementation? Well, there are a few things on the left-hand side that are part of computer science. The laws of physics, for one. I can't move information faster than the speed of light. It's not just a good idea, it's the law. There are also some algorithms that theoretically I may understand, but until I know how to write those as algorithms, I can't progress. FFTs, fast Fourier transforms, were such an example. It took a while for us to take the theory of it, the idea of shifting from one domain to another, and turning it into actually raw running code. A more recent example is the Viterbi algorithm, written by a gentleman by the name of Viterbi, which was the key to cellular communications. Pulling a signal out of the noise in a cellular noisy environment is hard, but the Viterbi algorithm made it possible. Those are the domains of computer science, and that's a good thing that we have people focused in that space. But you and I, we're software engineers, and we work in the realm of building new algorithms, turning theory into algorithms, taking those algorithms and making architectures out of them, building organizations that do so in a sustainable fashion that we make money on, and finally, on the most right-hand side, building systems that are right and good for humankind. Every line of code you write has a moral and ethical implication associated with it. Another way to look at this is the different kind of systems we build. So this is from left to right, moving across time. The earliest systems we wrote were largely mathematical in their nature. I have a simulation of a nuclear explosion. Go implement it. I've got a payroll system. Go worry it out. But then we started moving to symbolic systems, that those numbers mean things. They represent containers, they represent people, and I can start doing operations upon them. As we move to our more personal things, then the problem of human-computer interaction came into play. As we began to move to distributed systems at global scale, then scale became the problem. And now we're in the era of imagined realities, what Zuckerberg would call metaverses, although I actually both hate the term as well as loathe Zuckerberg, but that's another topic for another time. And that's where the issues of moral and ethical implications come into play. So depending on what you're building, you're going to approach it in very different ways. If I'm building a bit of disposable software, then I don't need no stinking code. I don't need no stinking diagrams. I just take a bunch of wood, go build it. And if my doghouse collapses and I build a new doghouse, if my doghouse really fails, and I just get myself a new dog. On the other hand, if I'm starting to build a system for which it's using my money and the stakes are higher, the risks are higher, you bet I'm going to worry about a little bit more discipline. I'm going to do some modeling. I'm going to do some architecting. I'm going to do some testing along the way. Most modern software development is what you see on the left-hand side. It's like city renovation. Imagine I'm an Elon Musk comes into the citizens of Paris and says, I'm going to build a hyperloop from La Défense to the Eiffel Tower. And most Frenchmen will say, oh, I don't think so, Elon, because you have a number of competing interests, historical, economic, practical, that are playing a role here. And so it is for all large software intensive systems. Google is a legacy software company. Facebook is a legacy software company. Pretty much every one of the FANGs is these days. And this is the nature of software development within them. Now, thus far, we've been talking about symbolic systems, that the world is changing. Most symbolic computation deals with lots of data, you're making models, yada, yada. But there's another way to look at it, and this is where AI comes into play. So let's see what's happening next. What is an AI? Well, for me, it's a very simple litmus test. If I have a system that reasons and that learns, then it's an AI. If it's only one of these, or if it's neither of them, then I've got something very different. The learning part's pretty important because it says I'm no longer programming my systems wholly, I am teaching them along the way. A little bit of history here. The earliest AI or ideas of AI came from Greek mythology. And you had an AI, I guess you could call it that, a golem that would walk around the island of Crete. He was made out of clay and he would throw stones at anybody that was intruding upon the territory. So the idea in our mythology that we could bring life to these machines. Da Vinci was even on the scene. He built his mechanical knight. War is messy, ugly, dirty, sweaty, bloody. And so the more in which you can pull people from the equation, the better it is. And so he devised this notion of these mechanical knights that would do the fighting. It continued to be part of our human psyche in movies such as Metropolis, Terminator today, and the like. And of course, Turing came onto the scene that says, let's formalize this a little bit. You know, we can call a computer intelligent if we can deceive another human. It's interesting that the idea of intelligence was wrapped around the idea of inception. In movies such as this, Her by Spike Jonze, it brought us to really kind of where our current psyche is today, building systems that are very close to human intelligence. Now, the first organic neurons showed up on Earth around 700 million years ago. So organic life has had a long time to evolve. It wasn't until I think the 30s or 40s to be projected that neurons actually were computational elements. They actually did some sort of processing. We have mapped the entire neural network of the common worm, some less than 10,000 neurons. And yet, even though we know the entire structure, it's not like we're awash in killer worms on the earth. We're missing some things. We have also mapped the entire neural network of the common fly. Here we're dealing with a few 100,000 neurons, but it's not like we've got, you know, cyborg flies that are irritating us. We're on the edge of mapping the entire neural network of the human brain. So neuroscience has come a long way, and yet we know we're missing some things. Brains in the lower right-hand side here, we're talking about a device that has 100 trillion synapses, 100 billion neurons running on 20 watts of power. If you happen to be a politician, it might be less power. We'll leave that for another discussion. But, you know, we sort of map that out. We don't know how to do that yet in our software systems. A lot of contemporary AI is about pattern matching. I've got these images, I want to classify things within them, I want to identify things. It's really inductive reasoning. But we haven't gotten to the point where we've dealt with decision making. Recommendation engines are kind of like that, but again, they're offering up mostly statistics, not really doing any decisions. Abductive reasoning, which is what Judea Pearl is focused on, are the issues of model building, and also causal reasoning, cause and effect kinds of things. So if you look at the history of AI, it has a very interesting flow, not unlike software, traditional software. Norbert Wiener, again around World War II, in his book God and Gollum, in his work on cybernetics, he in fact coined the term. He was mostly an analog kind of guy, taking ideas from what we perceived in control theory to intelligence itself. And it wasn't until back a decade or so later that these two guys, Simon and Newell, began to introduce the ideas of symbolism into AI. So the very earliest ideas of AI were symbolic in nature. They were trying to use formal logic. Now, around a little bit later, then we began to look at the processing power of neurons. This is the first artificial neuron called the SNARK, built by Minsky and crew. And obviously, this was not going to scale. But early neural networks didn't go very far, and so we began to build machines to mostly improve the symbolic side of things like the Lisp machine, the connection machine. Watson, in fact, was an amazing one in which we threw a lot of hardware at the problem. Watson was certainly an important AI development, but it wasn't on a neural network. It was mostly statistical AI around the time. On the other hand, you see devices that were beginning to pop up about a few years later, such as what was happening with Google and crew. And this is a chipset from NVIDIA, the Jetson Nano I mentioned. So you saw the rise of TPUs because in the deep learning world, there were common architectures that were emerging around TensorFlow and the like. Going even further, we've been able to take artificial neurons and squeeze them down into silicon so that back in 2018, IBM, demonstrated packing 10 to the ninth neurons within about the same space as a human head. Didn't obviously do what a human did, but we know we can bring it to that level. The AI community is interesting in that it's beginning to mature and rediscovering the same kinds of things we learned in software engineering some years ago. So we see the emergence of common patterns of neural networks, CNNs versus RNNs and the like. We're seeing the emergence of common architectures. The transformer architecture is the one that's behind GPT-3, that's behind AlphaFold, and it's become the dominant architecture for deep learning systems, and that's a good thing. We're also seeing that it's applied to common T's, and so Andreff is the gentleman who's the head of AI at Tesla. He's observed, if you're building an AI, the models and the code, it's just like any other production system. It's got configuration management, there are baselines, there are testings. It's just alive as anything else. So the good news is that the things we have learned in software engineering over the years, the agile methods and the like, they apply to AI as well. So what's happening is we're becoming to understand these common patterns. And you're going to have people that are going to continue to evolve that space. But for most of us, the problem is on this last bullet. It's less so the engineering of AI systems and more so the engineering of systems that have AI components within them. Both of them are computationally equivalent, but they have different efficiencies and different scalability and latency and the like. So now our problem is, how do I take our agile methods and introduce AI parts within them? That being said, the fundamentals always apply. There's a whole nother talk I could give you on software architecture, but this is the essence of it. You try to build systems that have crisp abstractions, a clear separation of concerns, a balanced distribution of responsibility, and simplicity. And the process is just this. This is the essence of the agile process. You grow a system through the iterative, incremental, and continuous release of its executable architecture. That's continuous integration, continuous deployment, continuous architecture. That's the essence of what we do. There's work to be done, and obviously, lots of software to be written, so these are exciting times for us, and that's cool. But let me leave you with this, and we'll have a time for a few questions. Think of it this way. Software is the invisible writing that whispers the stories of possibility to our hardware. Software is the invisible writing, and it whispers the stories of possibility to our hardware. And you are the storytellers. So thank you all. Here again is how you can reach me. Follow me on Twitter, email me, check out my web. And I think we have time for some questions. There we go. And we're back live.
Yes, thanks, Grady, for the excellent lecture. I think your last phrase was really inspirational. I think one of the greatest analogies is that we write code. So I think seeing ourselves as storytellers fits perfectly with this uh, analogy. Regarding the questions, first we have a comment here from one of our alumni, Marielle, uh, and she thanked you for the fantastic presentation and for emphasizing so many incredible women who contributed to software engineering. So it was more a statement than a question, but I think it's very nice to thank because, well, even myself, after seeing history of software engineering many times, you were uh, by far the best presentation about this subject. So really amazing. And we put in the comments your website, where I know that you document about the all of the steps of the software engineering history. So I leave the recommendation for everyone watching to check your website because there is amazing content there. Uh, One of our students from our Agile course asked more about the functional languages because he said, Guilherme said that we are having a boom of functional languages or a coming back, if we may. Uh, and due to that, uh, what do you believe are some advantages and maybe challenges that adopting functional programming for the software architecture?
Functional programming has found a particular ecosystem, a niche in the ecosystem of web systems. So let's go back to economics for a moment. You saw the move from mainframe systems to more cloud-like systems, and now particular architecture built around containers. Oh, let me point out the little device I have here. This is a little cloud, my own personal cloud, 4 Jetson Nanos running Kubernetes in that little space. It's pretty cool. So you see the migration of these web-centric systems at scale moving toward container-like architectures, and there's great economics around them because they allow me to have my teams develop independently. They allow me to release parts of it independently based upon microservices. They allow me to do balancing, all sorts of great things. But it's also led to the move toward serverless. What is serverless in effect? So prior to serverless, it was like you would pay per instance. So this is where the economics comes in to say, hey, I'm going to pay for X number of instances of a VM that I spin up. Serverless says rather than paying by instance, I'm paying by execution. So all of a sudden, you are now incentivized to build your systems so that you reduce the execution time upon them. And so we squeeze it into these little stateless kinds of things that actually do the real work. And that's all I get charged on. So there's been this economic drive that pushes me to serverless things. And those serverless bits are best described as functions. Now, keep in mind, that's still a small part of the system because you've got the entire other infrastructure around it. So serverless has found itself in this ecological niche, as you will, that it's an important part of the business rule side, the animation side of a system, but it's not the only piece of it. So yay serverless, yay functional programming, but you're not going to build a city out of it. It has a place.
Awesome. And regarding you talking about the economics of scale, we have a question here from Andre. Uh, and he asked that, do you think that the same economics of scale that have made us dependent on cloud-based architectures can made us dependent on AI, but with bigger ethics problems?
I think AI is going to be moving into the realm of simply being part of the atmosphere. So we see a lot of press around large language models like GPT-3 and the like. China has produced even a larger model around this time frame. But ultimately, while they're interesting, you want to get value out of them. And so they eventually get squeezed away into the back rooms. Recommendation engines are the first example of that. That you see recommendation engines all over the place. Originally, they were statistical in nature. These days, there's a little bit more, lots more deep learning associated with them. But you don't see the AI. The AI is just there as a functional piece to it. So by and large, I'd say, what's going to happen was what I said at the end. The problem for us as systems engineers is it's just a piece. And as a piece, I treat it as a piece like anything else. There are benefits, there are risks associated with it, and I will do what I can to engineer my system to maximize the benefits and reduce the risk. There will continue to be innovation in AI, absolutely, and that's where I'm spending my time. The reason I've got this cluster is I'm doing some work on artificial general intelligence, quite frankly.
Awesome. I'll make a personal follow-up question regarding this subject. I study my PhD more about this about intelligent systems in general and this challenge of making systems with AI, as you said. And what do you believe are some challenges of? Well, you spoke about them and how the AI field is now attempting to bring these ideas of software architecture to the world of AI. But what do you believe are those challenges? Because even if we have as a piece the AI inside our systems, do you believe? What do you think are the trade-offs that we are starting to understand about using those stuff inside our systems?
Well, I think part of it is the realization that AI systems have inherent biases within them, and they're biases that don't come just from the algorithms; they come from the data itself. If any as a community in AI has discovered or rediscovered the dark underbelly of humanity and the ways that our software systems can reflect the worst of us. And I think the realization as an industry that we now better understand that's a good thing. I don't know what policies are with regards to facial recognition and surveillance and the like. Every country is different. If I speak of AI ethics here in the United States, if I go to China, I'm going to get a very different view because they have a fundamentally different ethical foundation upon which they're basing their decisions. So the fact that we're discussing these things is actually, I think, a good sign. Don't have any answers, but at least we're talking.
Awesome. One of our last questions we have here is that we have another probably another subject, which is there is a lot of innovation on distributed trust in computing, such as blockchain, cryptocurrencies, and all those modern stuff. And do you think it will ever be more useful than
Ah,
today?
follow me on Twitter, and you'll see that cryptocurrencies and blockchain are one of my favorite things to talk about these days. Let's just politely say that. Well, I'm not even going to say it here. Follow me on Twitter. I don't own an NFT. I don't own any crypto, and I do so intentionally.
Yeah, I read some of her threads, and I'll use this opportunity to refer to everyone that they follow you on Twitter. We had the pleasure to invite you here today via message from Twitter. So
Yes, indeed. Indeed.
you are not lying when you say that you answer all your questions, and we can only
I
be
do indeed.
thankful about how open you were
You bet.
talking with us. So I think that's it for today, Grady. Thanks a
Yeah,
lot for
I
the
was
opportunity.
we would like to invite you to come to Brazil. I know we are not in Hawaii, but it's nice also. We have palm trees here also, you can see.
Yes, you do.
So
Yes.
you are more than invited. We will arrange something after the pandemic, and it will be great to host you here. It will be a pleasure.
I would love to come to Brazil. It would be a delight to do so. Thank you all. Stay safe, everyone.
Yes.
Thank you.
Bye bye.
Bye bye.
Bye now.
Bom, então é isso que temos por hoje, pessoal. Muito obrigado por todo mundo por estar presente na palestra. Foi uma super oportunidade receber o Grady. E não percam a chance de que nessa quinta-feira, também às 16 horas, nós vamos ter uma outra super palestra com o Eric Gama, inclusive foi citado pelo Grady durante a palestra, que é um dos coautores, né, do famoso livro Design Patterns, que vai falar um pouco para a gente sobre como a Microsoft, onde ele trabalha, está desenvolvendo o projeto do VS Code, famoso editor aí, muito popular atualmente, né, de forma aberta. Né? Então, acho que totalmente tem tudo a ver com o que a gente tem feito aqui na nossa, no nosso curso de software livre. Né? E também, só para fazer esse close-up, vou repetir essas coisas que eu estou dizendo aqui em inglês, para se tiver alguém assistindo conosco. So, thanks everyone for your presence here today. It was a pleasure to receive everyone for the excellent lecture by Grady. And please don't miss the opportunity to watch us on Thursday, 4 p.m., same time, when we will receive Eric Gama, one of the co-authors of the famous book Design Patterns, where he will talk for us a little bit about how his team on Microsoft is developing VS Code, the famous editor made by Microsoft, in the open as an open source project. So please don't miss this opportunity, because it's a perfect fit for our Agile course. And thanks everyone for your presence today. And please give a like in the video, share the channel, follow us on the social networks. It's very good because we are trying to bring all those specialists. E é isso aí, galera. Então, tipo, não esqueça aí, pode deixar a curtida no vídeo, se inscrever no canal e adicionar. A gente precisa terminar o vídeo com todos os clássicos para vocês não esquecerem, porque a gente vai tentar continuar trazendo conteúdo com tantos especialistas, com tanta gente super bacana. Então, muito obrigado e por hoje é isso aí. Tchau, tchau.